As I said yesterday, we're looking here at something which is a very important topic for post-secondary. And I think there's going to be about 10 different examples that we do over the next 4 days or so. So it's not necessarily broken up into part 1, part 2, etc. in your notes. But the whole lesson, which covers many pages, is punctuated by a point where it says, do these questions. And then we do some more examples, do these questions. So we're going to be solving problems that involve what are called related rates. And related rates are exactly what they sound like. They are rates that are related to each other. Okay? We're going to dive right in. Number 1 says a circle is changing its size. Why would this be happening? Well, maybe there's a snowball that's sitting on the floor and it's melting, and you have a puddle that's circular that's growing. Maybe there's a circular puddle of water on the floor or the sidewalk outside and it's evaporating and it's shrinking. Maybe there's an oil spill. A tanker's bladder has been ruptured and the oil is spilling out and it's spreading out in a circle, as things do that are liquid, and it's growing. Okay? It doesn't matter why this is happening. But when a circle is changing its size, we can imagine that the circle is increasing. It can even be something like I drop a rock in water, there's a circular ripple that's growing. When that ripple grows out and the circle grows in size, 2 things are changing. The area is changing and the radius is changing. And what this question is asking is, what's the relationship between how fast the area is changing and how fast the radius is changing? And it seems like an impossible question. It seems like there's just not enough information here to be of any value. However, to begin with, I want to just back up for a second and tell you that in this section, rates are always with respect to time. And we've talked about this before. Right before we wrote our exam, I said, I don't know the exact examples I used, but I said when you talk about rates of change, whether they're average or instantaneous, they are typically things like the rate at which I eat chicken wings is so many chicken wings per hour. The rate at which money is spent is maybe so many dollars per day. The rate at which energy is being used in my house is so many kilowatt hours. I shouldn't do that. That's a weird unit. Is so many joules per second. So in this question, what you were asked for is the relationship between dA dt and dr dt. The question is, how are these related? I mean, if the area of the circle is increasing, the radius is increasing. So this dA dt is going to be a number of, square centimeters per second if the area is measured in centimeters, right? And this is going to be a number of centimeters per second because, presumably if the area is measured in square centimeters, you want to be consistent and measure the radius in centimeters. I'm going to just introduce this in a gradual way by asking you a question, and the question is this: is this a reasonable statement? The first statement is this: the area of the circle is related to the radius of the circle. I hope that's obviously yes, reasonable, because there's actually a formula connecting the area of a circle to the radius of a circle, isn't there? A equals pi r squared. Okay, so it's absolutely a fact that the area is related to the radius at any point in time. Well, if those variables are related, doesn't it make sense that the rates at which the variables change will be related mathematically somehow? And I'm making a distinction here between two relations. A and R are related. These are related variables. But since they are related, dA dt and dr dt must be related as well. There's a relation. That's what related means in math. Okay, well, these things that I'm going to highlight are related, and they're rates. This is why we call it related rates. The question is, how are they related? And it's a very simple question once you're shown how to figure it out. We start off with writing out the relationship between the variables. Okay? That's the relationship between the variables. And again, if they're related, their rates must be related. The question is this: how do we, and I think some of you might be able to come up with the answer to this, how do we all of a sudden go from that to something that has rates of change with respect to time? How do I go, and I feel as though this might almost give away the question. How do I change this so that it's not A equals, but it's dA dt equals? Jack?
Substitute r for the derivative of dr dt and then take the derivative of area.
Okay, I'm just going to end with the last 5 words you said. Take the derivative of area. In order to go from area, because I think you know what you mean and I think I know what you mean, but I want to focus on the last part that you said. I need to take the derivative of area to get dA dt. But what am I differentiating area with respect to achieve that?
Do you have to switch the radius with time, so you're differentiating with regard to the variable time?
Right. Normally, and at first I didn't quite get your drift, but I have it now. Normally in the past, and please don't write this down, if you just walked into an exam, and you actually did this on the written response question on the exam, the 4th one, and I said differentiate, you would assume I mean with respect to r, wouldn't you? You would say, oh wow, dA dr equals 2 pi r, and you would be done, right? What you said was we need to switch r with t, and correct me if I'm wrong, you meant what that means is we're not differentiating with respect to r, we're thinking of t as the variable. So when I say to you, what is the derivative of a with respect to t, this is where we all of a sudden magically out of thin air, we introduce dA dt. We go, well, I'm going to differentiate with respect to t. But if I differentiate this side with respect to t, then I have to differentiate this side with respect to t. Now, r is a variable. What's the derivative of pi r squared with respect to t? Will?
2 pi r dr dt.
Excellent. I wrap the exponent around the variable. This becomes 2 pi r, but we're not differentiating with respect to r. It's to the 1. That goes unsaid most of the time. We're not differentiating with respect to r. If we were, then the derivative of pi r squared with respect to r would be 2 pi r. We're differentiating with respect to t, and since r depends on t, we have to multiply by the derivative of r with respect to t. It's implicit differentiation everywhere. And that's the answer to the first question. There's the relationship between the rates of change of the variables, and this up top here is just the relationship between the variables at any point in time. I want you to notice that, I won't do that yet. Any questions with that example? All right. If the radius is growing at 3 centimeters per second, then how quickly is the area changing when the radius is 12? So what this question is saying is dr dt is a fixed value of 3. Maybe it's a computer simulation and we're increasing the area of the circle by continually increasing the radius, the distance from the center to the edge of the circle, at 3 centimeters per second the whole time. I'm going to put the units here. I have a question for you that you might wonder why I'm asking it, but I think it's important. You have a circle that's growing and the radius is increasing at 3 centimeters per second. Are you with me? So at some point in time, the circle is this big. At some later point in time, it's bigger, and at some later point in time, it's bigger. My question is, I'm just going to go with 2. We'll use these 2. My question is this. Let's imagine that the circle started even smaller than that smaller one. This point is moving away from the center at 3 centimeters per second. Would you agree at this instant in time where we're looking at the center circle, maybe it's a ripple, that the area is increasing? My question is this. Who can explain to me why the area will be increasing at that point in time when the ripple is that big, but it will be increasing more? The rate, the dA dt here of the circle will be bigger than the dA dt here. Isaac?
Would it be because the perimeter, or no, the circumference of the circle is bigger than the smaller one? So
Sure.
Expanding, it gets larger area quicker?
Right. And I realize we're talking about instantaneous rates of change, but we can think of that increase of r as being, I think this might do it. We can think of that increase of r as being a certain thickness being added to the circle, right? In a certain period of time. But if I add that same thickness to the circle when the circle is bigger, I'm going to be adding more area. And what I'm getting at is dA dt not only depends on dr dt, it depends on r. And that's exactly what the formula predicts. dA dt is connected to the radius and to the rate at which the radius changes. Anyway, we can answer this question now. dr dt is 3. We're trying to find dA dt. So we had our formula, A equals pi r squared. We differentiated it to get dA dt equals 2 pi r dr dt. And we say, well, what else do we need to know? Well, we need to know the radius to calculate dA dt. But the radius is given. You're told the radius is 12, so we're simply going to put those numbers in. dA dt will be equal to 2 times pi times the radius of 12 times dr dt of 3. I hope you appreciate that I put positive 3 because the radius is growing. Okay. And if you want an exact value, we can write dA dt equals, help a fellow out here, I'm pretty sure it's 72 pi. Okay. Now, what are the units? Well, we don't typically go for writing units everywhere in math. That's a science thing. But this is centimeters, and this is centimeters per second, which means, of course, this is square centimeters per second, which matches what we're finding. And if you want a decimal value, then feel free to take your calculator and go 72 times pi and get 230 whatever, or I don't know, okay? You can work it out, 220 something. I think everybody understands that this is not a very practical answer. If you were an engineer and you wanted to know at a particular point in time how many square meters of oil are being added to the spill, and you're the engineer and you say to the people who are trying to clean it up, oh, it's 72 pi. They're smart enough to know what you mean, but 72 times pi is a more informative number. Would you agree? Okay. What if the radius is decreasing at 4 centimeters per second? So this is a different question. This is a puddle of something evaporating. It's not a ripple traveling out. Well, we still, I want to go back to the beginning here to try to train you to what you do. In this question, you have a dr dt of -4, and you were asked to find dA dt, right? Just imagine that this question stood on its own merit, and it just said, a circle's radius is decreasing at 4 centimeters per second. What is the rate of change of the area when the radius is 15? What you would do is you would say that I have a rate of change that I know, and I have a rate of change that I want to find, and then you would say, what are the variables involved? And you would say, well, one of the variables whose rate of change I know is r. The other variable whose rate of change I want to find is a. Your problem now is, how are those variables related? A equals pi r squared. Then what you do is you differentiate it to get a usable relation that you can use rates of change to calculate rates of change. And we've done all this already. I'm just pointing out that that's going to be the procedure. Oh, see? And you're going to slip just like that. We're not finding dA dr. We're finding dA dt. Equals 2 pi r dr dt. And again, we've already done this. So the bottom line is you put in the numbers. You put in the radius of 15. You put in -4, and you work out what this is, and by my count, that's -120 pi. To determine the units, you do not have to look at the units in all your work. You can just say that it was a rate of change of area, which would be dA dt. And that means it's units of area over units of time. It's centimeters squared per second. Are we okay with C? Okay. Now, you might look at example 1 and go, well, what real life application is there? And, you know, I admit the thought of the oil spill is kind of a, nobody really cares, let's just clean it up, right? It's not a very practical calculation. It doesn't help them. But in engineering, particularly in physics, and very often in chemistry, and sometimes in bio, we use rates of change for a very real reason. You don't learn this formula in Physics 30 anymore. It's a real shame. You learn about potential difference, which is voltage. You learn about current. And you don't talk really about resistance. I mean, I talk about it in my class when we talk about increasing a magnetic field. If you have less resistance, you have more current. But we don't really use a formula. This is called Ohm's law. And at any point in time in an electric circuit, there's a voltage that's being applied to the device, whether it's a light bulb or a resistor or whatever. And there's a current that's being produced, and there's a resistance. Voltage is measured in volts. Current, which is I, don't ask why we use I couldn't tell you, to be honest, is measured in amps or amperes, and R, which is resistance, is measured in ohms. And the unit of these is a volt, an amp, and an ohm. It's a Greek letter, omega. And what typically happens when you first learn about this formula in science is you just do simple calculations. But the fact of the matter is, devices heat up the longer they're used. And the more it heats up, the greater the resistance. So what happens is, as soon as you turn it on by adding a voltage, everything starts changing. But they always obey this law. These are all three variables. What is the relationship between dV dt, di dt, and dr dt? What's the relationship between the three rates of change of the variables? Well, this goes to what I talked about a minute ago, which is that the three variables, listen carefully to the language I use because I'll use it all the time. The three variables whose rates of change we're interested in must be related. Those three variables are related by V equals IR. So if we want to take that relationship and turn it into a related rates relationship, we differentiate that with respect to time. And what are we going to get? Well, V equals IR. Oh, by the way, I meant to mention, I make a big deal of the delta in Physics 30. We don't need the delta. V equals IR. Well, the derivative of V with respect to time is dV dt. I'm going to write something down, and please don't write it down because it's horribly wrong. But why is this wrong? Why can't I do that? Yeah.
Because they're both like variables, so you have to use the product rule.
Right, they're both variables. I have to use the product rule. I can't, as I've said before, willy-nilly just start differentiating stuff left and right. I have to follow the rules. And this is a product of two variable functions of time. So I differentiate the first. I multiply by the second, plus I differentiate the second. I multiply by the first. There's the relationship between dV dt, di dt, and dr dt. So, for example, if I want to find dV dt, not only does dV dt depend on di dt, it depends on dr dt, and it depends on r and I as well. And the nice thing about this is true, right? This is true. This is a physical law. And this is true. And the reason this is true is we didn't violate any mathematical laws by differentiating with respect to time. So we've come up with an equation that electrical engineers use to solve problems. The problem now is that was A. B says if the voltage is changing at a particular rate and the resistance is changing at a particular rate, what's the rate of change of the current when the voltage has a value and the current has a value? Again, everybody, I want you to listen carefully. You have to graduate at some point to this point. If V equals IR, what's the answer to this question? You are not going to be led by the hand and told, find the relationship between the rates of change. That's going to be the first part of how you solve related rates problems. But we've already done that. And I have dV dt equals di dt r plus dr dt I. Am I correct? Okay. What do we know? Well, we know dV dt is 2.2. dr dt is 7. I really should change this question. They're both increasing. Okay, I really should say how they're changing. And we want to find di dt. If you just look at this formula over here, we're going to just start putting stuff in. dv dt is 2.2. di dt is what we're asked to find. Ooh, I don't know. Do we know the resistance? We don't know the resistance. We'll come back to that. Plus dr dt, well, that's 7. And times the current, which is 2. Man, we're missing the resistance. So how do you find the resistance? Well, you use any formulas available to you. You are told that the voltage is 12 and the current is 2. And you know that V equals IR. So you ought to be able to calculate R. It's 12 volts divided by 2 amps, which gives me 6 ohms. Do I need to write that down? Rearranging or putting those numbers in? Okay. This is just a linear equation, everybody. What you have is 2.2 equals di dt, which is what we're after, times 6 plus 14. So you have to take 2.2 minus 14 and then divide by 6. You get negative 1.97? Good. So at that instant in time, di dt is negative 1.97 amps per second. At that instant in time, the current load in the circuit is decreasing at about 2 amps per second. Any questions with that one? Oh, that's from last year. Do you know what that is? No? Thank you. I'm here all week. What about this one? Do you know it? Ohm on the range. We could spend all day working on those. Let's move on. Example 3. A triangle is changing its size. How? I don't know. Maybe it's changing its size because it starts off looking like this, and the height is changing. Okay? Maybe it's changing its size because it starts off like this, and everything is changing. Maybe it's changing its size because one side is shrinking at a certain rate and the other side is growing at a certain rate. Never tried this before. Nope, can't? Come on, really? Oh, that's a ripoff. You can only do one at a time. Anyway, it could be changing its size for a number of reasons. What's the relationship between dB dt, dH dt, and dA dt? Well, I'm going to go back to a triangle that's reasonable in terms of area equals base times height divided by 2. So if this is our triangle, and it doesn't have to look like this, this is the height, this is the base, and the area is the area. You don't even need a picture to do this. If you want a relationship between dB dt, dH dt, and dA dt, then you need a relationship between these three variables. By the way, your textbook sometimes uses A for altitude instead of height. I don't like that because we also use A for area. So the formula is A equals 1/2 base times height. And by the way, I didn't photocopy it for you today, but you will get a formula sheet that's just geometry formulas. You don't have to know these. So let's differentiate. dA dt equals, well, I need to use a product rule here. 1/2 the base is a derivative of 1/2 dB dt times the height, plus the derivative of the height, which is dH dt, times 1/2 the base, is our relationship. Derivative of the first times the second, plus first times derivative of the second. If the height is increasing at 4 centimeters per second, and the base is decreasing at 5 centimeters per second, what's the rate at which the area is changing at a particular point? Now I want to highlight something, and I held off on telling you this because I didn't want to overload things at the beginning. The values of the variables in a related rates problem. So, for example, if we go back and take a look at 1b, this radius of 12 centimeters can never be used until you differentiate. Then it can be used. You can put the 12 in here. You don't want to start putting the number in before you differentiate. Okay. We can't use the 15 until after we differentiate. You can't use the 12 volts and the 2 amps until after you differentiate. And the reason why is I don't want you to think you could do this in this question. Would you agree this is a true statement? Up here I look, I say, oh, the current is 2. Do you see where it says the current is 2? This is a brutal mistake. And then you differentiate that. Because the current is changing, you can't put in a value for it at the beginning. You have to wait until afterwards. And that's why when I do these questions, I make this list of rates of change, and I don't include the variable values. It's my way of reminding myself I have to do this first. So, let me write this out again only because I have to, because I don't see it. It's dA dt equals 1/2 dB dt times h plus dH dt times 1/2 b. Am I right? Okay. So we want to find dA dt. It's going to be equal to 1/2 dB dt, which is -5, times the height. Do we know the height? Oh, when the height is 12. This when the is the key or the clue that you don't put it in until after you differentiate. So the height is 12 plus dH dt is 4 times 1/2 times the base. You're told the base is 3. Well, you just have to crunch some numbers here. I want to say -24. A few people nodding. So dA dt is -24. It's a rate of change of area, centimeters squared per second. We have one more question, correct? I'm trying to warm you up to related rates by understanding the concept of related rates. We're not so much worried about the types of questions just yet. This question, if you want to talk about types of questions, appears to be the same type of question as the previous one. We have an area and a height, and things are changing, but the difference is the base is constant. So if you start off, and it's not a wild ride, but this is going to be a little bit of a journey. If you start off with this, and you do what we just did, which I'm not even sure you need to rewrite it. It's right there on the same page, I believe. Again, I'm just going to ask for confirmation. I didn't do it from memory. I differentiated again, but I want to make sure it's done right. If you had this problem, and we have a dA dt that we've mentioned, and there's dB dt, and there's dH dt. What is dB dt in this question? It's 0. We actually know it. I know most of you looked up there and said, well, I don't have any numbers, but it says the base is constant. So if the base is constant, this is 0, but that means that dA dt, that's gone, is 1/2 b dH dt. You with me on that? You did not need to do this to determine that. Because if the base is constant, your function that you start off with, or I better call it a relation, that you start off with is area equals 1/2 the base times the height. Correct? But the base is a constant. If the base isn't changing, the base is a constant, which means that's a constant. What's the derivative of a constant times h? The constant times dH dt. No different than the derivative of pi times r is pi dr dt. So be careful here. We didn't put in the constant value for the base. That's not what we did. We just said it is a constant. We could have. If you knew the base was 12, you knew the base in this question was 12, could you put 12 here and say this is here and say this is 6? Sure. And then you'd have a equals 6h. So what you're doing is this, and I'm going to leave this up here. You're going to see it again and again and again. You're developing an equation that contains variables whose rates of change you either know or want to know. So for example, if I take a look at this question, the side of a square is changing at a certain rate. That's a rate of change. What is the rate of change of the area? Okay, your first step says find an equation that contains the variables in those rates of change. What's the equation relating the area of a square to the side length? A equals s squared. That would be your first step. What do you do with that? Well, you turn it into an equation that has rates of change by differentiating everything with respect to time. Then you answer the question. Then you solve it. So, we're just about done here. This would be dA dt equals 2s ds dt. Answer the question. Put in everything you know and find what you're asked to find. The problems will get more challenging, but for the time being, you can see what your assignment is. And again, I'm going to leave this up here. If you want to write it down, you can. If you want to take a picture on your phone, you can. If you just want to look at it throughout the class, you can. I hope that made sense. You still have about a half hour here, a little bit less than a half hour to work on these. So get started. And Braden, make sure if you have any questions, let me know in the message window, and I'd be happy to help you out.